Hey there, ladies and gentlemen. We're going to go over the answers to part A here. Hopefully it goes really well. Um, the question one was pretty odd at first. I think a lot of people read that one, had to read it 2 or 3 times. We have the moles of pH 3 that's being consumed, the volume, and the time. We're supposed to talk about rate, and rate is the change in molarity per time. So we have to figure out the change in molarity of the pH 3. So let's look. I took the molarity, the moles and the liters, and I calculated the molarity. And then I just divided it by the time. Moles per liter per time. That's the units for rate. It's decreasing by 0.0024 molarity per second. And then for the other two, you can just apply the mole ratios between the two compounds, the one that we found and the ones that we're looking for. So that wasn't too bad. And then in number two, just scroll up a little bit more. In number two, we're doing the same thing, except we're not supposed to actually do any math. We're just looking at the mole ratio between the two compounds in question. It's a 2 to 3 ratio. So ammonia would be produced at 2/3 the rate of hydrogen. Not too bad. In number three, we are looking at these three rates. All three of these rates have a common factor of 0.0040. It's a lot easier to see that if instead you look at this as 8, 12, and 16. 8, 12, and 16 are all divisible by 4. Um, so I divided them all by 0.004, and I was able to see the relationship between the three compounds. That relationship should represent the the coefficients. In number 4, we're looking at some elementary reactions. Elementary reactions are straightforward reactions. They only occur in one step, which means whatever the reactant is directly impacts the rate. There's two reactants, so they're both in the rate. None of these were second order with respect to a particular reactant, but if they had been, if this had been a 2 here, then that would have been, squared. But they weren't. They're all just straightforward, easy reactions where the reactants are represented directly in the rate. Number 5 is a bit trickier. Even though it's a 3-step reaction, only one of the steps matters because it's so much slower than the other 3 steps. And that first step only has one reactant, so that one reactant is the only one that shows up in the rate. And some other examples in the notes, we talked about, well, what if the second reaction hadn't been fast? What if it had been slow? Then we would have seen the first reaction and the second reaction would have both been reflected in that rate. B throws some people off. B is just saying, hey, what if I add all 3 reactions together? What is the total reaction? And there's several things we can cross out of this reaction as we go along. Like this CH4H9 is made and then used, and then same thing occurs with this compound here, which has no name that I can fathom. The C4H9OH2 plus is made and then used. When something is made and used, like those two compounds are, we call them an intermediate. So that's actually the answer to C, is that those two pieces are intermediates. They get produced halfway through a reaction and then used up later on in the same set of reactions. Conversely, you may occasionally hear of something called a catalyst. A catalyst, you're probably immediately saying speeds up reaction or maybe lowers the activation energy, and both of those things are true. What a catalyst does in terms of these mechanisms is a catalyst appears usually in the first reaction, and it causes this reaction speed to be faster. And then later on in another reaction, that catalyst is then produced again, and so it gets used to speed up a step and then produced by a later step, so it doesn't actually disappear. It gets involved in the reaction and then gets produced by the reaction. So it's kind of like an intermediate in the sense that it cancels out of the overall mechanism because it's before and after, but it actually changes the speed of one of the steps. um, so now we're on to B, and this one's largely focused on units. Let's look at the basic rate equation. Rate is equal to K and then molarity to some power. The units for rate are always based off of molarity and time. Molarity and time. And for the rest of this question, I pretended that time was in seconds. I pretended that because to see t to the -1 is kind of weird. So I usually just use seconds as the base time unit. It could be any base time unit. It could be any time unit though. Minutes, hours, days, mega days. No, not mega days. But it could be any time unit. Just depends on how fast or slow your reaction is what they would use. So if the rate is in molarity per second, and this component is some factor of molarity, then the units for K have to kind of bridge the gap between the two. So what I did is I just took these values, 0, first, second, and third, and plugged them in here where the question mark is, and then figured out what K would be to make the two sides equal. Number 2, this one is a whole lot like what we're going to see in our quiz. We have to figure out what order the NO and the Cl2 are. We do that by picking a spot within the reaction data, and comparing how the molarities are changed. In the first two reactions, NO is not changing, but Cl is changing, it's doubling, and we see the rate doubling. So if chlorine doubles and the rate doubles, that means that chlorine must have a direct impact or first order impact, like I put there. Then I would not cross off, but I would mentally mark off those two chlorine values because they're the same. And then I could see that the NO is being doubled. The rate is being more than doubled. The rate, as the NO is doubled, the rate is quadrupled. Well, that means that the NO has a squared impact or second order impact on the reaction rate. So after going through those two pieces of logic, figuring out how Cl impacts the rate, figuring out how NO impacts the rate, we have written our rate law. The next process is to solve for K. And you can pick any one of these three reactions, plug in the values, and get K. Now personally, I like to then test that value in one of the other two that I didn't pick. So I would pick maybe the first reaction. I'd plug in, zero point 0.1, 0.1, and this K, and make sure that my rate came out correctly. And I can do that in my head actually. 0.1 squared times 0.1 times 180 is going to come out to 0.18. One thing I love about these rate law questions though is once I've got that K, I can immediately test it, and I feel good about my answer pretty quickly. Number 3, worksheet B, similar idea. I'm going to pick a spot uh, and compare what's happening to the rate versus the molarity. I would probably pick the middle two reactions because I can see that the rate is going from 1 to 2. I would ignore the 10 to the 16th because they're identical values, so they cancel each other out. So I have the NOCl is doubling there. Look at these values. I have 26.6 over 6.64. Yeah, I know that doesn't actually say 26.6, but if you think about, let's, come on, that didn't work. There we go. So this is actually 10 times bigger here. That's 10 to the fourth, isn't it? Since that's 10 to the fourth, um, it's 10 times bigger than the number below it. So I really think of this as 26.6 compared to 6.4. And anyway, after all that discussion, we see that the one value is actually 4 times bigger than the other, so we see that NOCL is squared. And then I can plug in, this maybe this one and that one, and I could solve for K. The K has some very funky units this time, because this rate is in molecules in cubic centimeters. So K has to kind of cancel some things out there. This was also in molecules in cubic centimeters. They both were. So to make the two sides equal, K ends up having per second per molecule in cubic centimeter, which made this dimensional analysis question a little funky. We have cubic centimeters are on top. This is molecules to the -1, so that's really on bottom. And we're trying to change it into units similar to molarity. So I had to get rid of molecules using Avogadro's number and converting it to moles. And then I had to use the relationship between cubic centimeters and liters there. If you don't know, cubic centimeter is actually a milliliter. Yeah, cubic centimeter is actually a milliliter. Question 4 is also a data-driven one. This one's a bit harder. Um, let's start off with the iodine. You can ignore all this for right now. We'll come back to that in a minute. But the iodine here is changing. OCL is not changing. And we see the change in the rate. So we compare those values. When the iodine doubles, the rate doubles. That tells us that there's a direct relationship between the iodine and the rate. So then I know that iodine is first order there. Iodine doubles, the rate doubles, iodine is first order. Solving for the OCL is going to be a lot harder because none of these values for iodine are the same. So we're like, which one am I going to choose? So one method that you'll see is they'll write one reaction rate over the other reaction rate and fill in everything you know. So the only thing I didn't actually fill in is I should have written this value for the rate, this value for the rate, but I picked rates 1 and 4 on purpose. Well, look at these two rates. Those are the same. So these two rates would cancel each other out, and this would be equal to 1 over 1. K would cancel out, all right? And then we have 0.12 and 0.24, both to the first power. That's the same as 1/2. So how do you get 1 equals 1/2 times what? 2. That's what's going on here. That is 2 to the first. So that's how I figured out that the OCL was to the first. I thought that one was really hard, a little bit too hard. It's not that it's undoable, it's just it's a little bit too much to figure out the rate law. Now that I do have it figured out though, finding K is pretty simple. I'm just going to throw in one of the sets of data. I picked the first set of data and I solved for K after plugging it all in. And part C was easy too. I said, hey, pretend that they're both 0.15. What would it look like then? So you're going to plug 0.15 in to both spots and K in there, and you solve for the rate. All right, this is where we're stopping. We're actually stopping on B for right now. You guys are going to take a minute here, think about your reaction rates, and then the quiz is coming out. Good luck, and I'll see you soon.